Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today we're going to review a power supply, but while we review it, we're going to use it to try to revive a little 12-volt battery, okay? Got a little 12-volt battery from a friend who, goes in one of those little toy cars, and it's discharged like to the point where it might be dead. But we'll see if we can revive it, okay? I think it's down around 2 or 3 volts. So we'll see. And I'll kind of show you how you can charge a battery with a power supply. But this is from Nice Power. Let's open up. Now, the thing that's special about this that makes it a little different, say, from my Kaiweets up here, which these are really good buys. And those things are 30 volts, 10 amps. That's kind of a common high-end range, 300 watts. You find a lot of power supplies 5 amps. But 10 amps is kind of the higher end. And then every once in a while you find a 60 volt one at 5 amps or 10 amps. And they actually, I think they have a 60 volt 20 amp. This is 30 volt 20 amps. Yeah, the 60 volt one was out of stock because that would have been nice to have one of those. But anyways, so let's open this up, take a look at it, and see what you think, okay? Oh, and just to be clear, they did send this for free for me to review. That's how I get stuff, that people give it to me. I've never been paid to, review something. And I've only had, of all the things said to me, I've had a couple companies say, oh, can you send the video for us to review before you post? I'm like, nope. I say, yeah, just don't send it to me if that's what you want. And they said, no, we'll send it to you. So I'm never asked to say anything, or I think one time I was supposed to say their name. So that's easy to do, right? That's pretty fair. But and also to share links with you guys. The Kaiweets stuff, they give 15% off for viewers of the channel, KA15, so use that. The link's always down below, but I'll look to see if I have a link for this one, okay? A discount link. But otherwise, let's open this bad boy up and take a look. All right, so this is the power supply, and you can see we have the red, the black, and a green. I'm sure that's tied to chassis, right? And rarely use those things. There's only 2 knobs, not a fine and a coarse, so we'll see how that works. On the back, we have our IC plug, fan, and some connections, some big girthy guys on the back. So, wow, okay. And the other thing, just a manual and some power leads. So, all right, let's power it up. All right, this is the battery, 12 volt sealed lead acid. Okay, let's check it out, see what voltage we have on that. Okay, so this looks actually even worse than I thought. It's under 1 volt. So, yeah, it might be beyond recovery, but you know what? Let's give it a try. What the heck? All right, so let's go check out the power supply first. I just got the leads on the power supply tied to the multimeter leads up here using that nice X-Tech meter. Okay, let's go ahead and power this thing on. Now I can see in the camera this is like jumping all over the place. It's actually really solid, so sorry about that. But yeah, I like to have a load on off, or off on, as far as power to the load. But yeah, it's just pretty simple. Power switch on. Now it's cranked all the way to the highest voltage. Yeah, that's pretty fine tuned. I was wondering about that. Now sometimes if you move, okay, what I was going to say, sometimes on these kind of knobs, if you turn them fast, it accelerates the power here. So, you know what, hold on a sec. Let's see if I can fix this thing. All right. Yeah, that still looks weird in the camera. I think it's funny. It must be the way the control chip powers up the LEDs. Yeah, I don't know, but in visible light here, it looks nice and solid. All right, so anyways, yeah, they're both down close to 0. This says 0.079, that's 0.00. Let's turn it up just a little bit. Okay, 0.27, 0.266. I just want to see if they're going to track so we can trust this when we do the battery. I think I'll still do the, there'll be some voltage drop across the cable, so I think I'll still look at the voltage over here. So I guess here we'll go up to, yeah, they look like they're tracking pretty close. I'm going to turn it all the way to the max to see if it drifts off much. 3101, 3111. Looks pretty good. Okay, guys, so this is how I set up the current setting. So when you charge a battery, you want to set the current for maximum current input, especially when you're dealing with the battery like this. You don't want to overheat the battery. So I'm going to set it for, I think I'm going to set it for 1 amp. And the way I do that is I short them, the terminals, and then I start bringing up the voltage. And let's see what happens. Oh, whoa, it's up to 6.8 amps. I'm going to drop it down to, down to 0. Wow, it jumped right up to 3. I think there's a lag from the time I turn this to, yeah. You have to wait a second. It is pretty, okay, 1.2 amps, that's good. So I'm going to go ahead and start there, okay? Then I'll start the voltage at 0, and then I'll pull up the voltage where this is drawn max current, say around 2 or 3 volts, something like that. Well, I won't really be able to tell because the battery will pull more than 1 amp. It's a 7 amp hour battery, so it'll pull more than 1 amp. It should, unless it's a really bad battery. And when it does, it'll make this voltage collapse down to, close to 0. Well, whatever the voltage is of the battery. So let me set that up. All right, I'm set up. So I've got the terminals from the power supply up here, kind of clamping in the voltage leads. And there we are. It's 0.1 volts. This is really bad. And down here it says 0. So we're going to bring up the voltage a little bit. And the voltage is coming up. The current's not even started flowing yet. Well, that's interesting. No current flow. Wow, that battery is in bad shape. There's no current flow, and it's allowing me to take the voltage up. Oh, now there is. Okay, once I got 3 volts, it started to pull some current. That's pretty crazy. Okay. And, the internal resistance is high enough that it's not pulling a lot of current. Battery's nice and cool. I mean, we're only taking in about 1 watt in that massive thing over there, so we should be okay. Now, if this let me, what I'll do is I'll just take up 12 volts and it'll just take the current up. Let's see if it'll do that. No, look, wow, isn't that crazy? Wow. Well, guys, this is kind of crazy. I've played with this, taken it down and up a few times, and doing it the first time with you, seeing a little current flow was the best I ever got. It just, I've seen batteries where they short internally or they just draw a lot of current and maybe they never come up to voltage, but I haven't seen one that was just open like this. Let me know in the comments if you guys have seen a lead acid battery that is, look, a little bit of current right around 3.75. Now, if I leave it here for a moment, see what happens. What I've seen before is it just drops back down to 0. Now, when initially, when I think it was over 5 volts, it just went down to 0. Yeah. So, okay, now it popped back up again. Wait, that's kind of crazy. Maybe I'll let it sit here for a minute and see what happens. All right, guys, it was 0, and I just thought, well, what the heck? I brought up the 12 volts, and then all of a sudden it started pulling current. Now, it's hit my maximum current, so now it isn't constant current, where before it's constant voltage because it's regulating voltage. Now it actually is trying to charge. It's got like 10 watts on it. I'll monitor the temperature on this thing, and yeah, and just keep track of it, and let's see what happens. But so starts off constant voltage until it meets the current limit that I set, and then it goes to constant current. And then if it did charge up to that 12 volts, it'd go back to voltage, and it would sit there at that voltage I set it at. So then that way you don't go over voltage. All right, guys, so it's 7 volts here. I turned the current down just slightly, just playing around, but I'll take it up to about 1 amp again. Now, if I take the voltage up higher, I can go up a little higher. It's charging a little bit. And watch this, constant current. If I drop the voltage, and it goes constant voltage. So that's where the battery's charged up to now. So that's interesting. If I take out one of these leads, yeah, see that? Now it starts to drop quickly, but it's up. Well, it dropped down. Yeah, so it's still dropping. So I just put this back in, and it gets charged right back up to 7 volts. So it's still constant voltage. So if I take this a little bit higher, we'll say go to, okay, just over 8.8. The went to constant current, so I can go a little bit higher, and we'll just see. So it seems like it's starting to take a charge. So sometimes your chargers that come with these things, if they get discharged too low, it'll say it's unsafe, I can't charge. The charger's just not designed to handle that, which is kind of a crummy charger. But you know, low cost things, that's the way they come. Sometimes you get better chargers, and they'll put a pulse charge, or they'll do a low trickle charge or something. But a pulse charge, that way they can put the voltage up higher, and they can pulse it and pulse it and pulse it and try to get that voltage to come up. Once it comes up, then they can start to charge at what current level that the charger is set for. So let's say if you had a 10-watt charger, we're almost there right now. But if you had a 7-watt charger, it wouldn't do it. But now, we're getting up closer. Now, it could be you got a 10-watt charger, but it doesn't want to put out more than so much current because it's expecting to put out that current at, say, 10 volts, not 7. So there we go. Okay, so I'll bring you back when we get up a little higher. All right, guys, so we're still sitting here charging. So we're going to move on. Okay, so I got a scope probe here, and you can see the voltage here, right? It is 6.6 volts, but you might be able to see that little bit of little noise there, right? It looks like some digital noise there. So let's go ahead and put this signal right in the middle. We're going to put this on AC so we can look at AC ripple, and we're going to increase we're going to 500 millivolts, 200 millivolts. There we go, 100 millivolts per division. And let's spread that out a little bit. Okay, so I'm going to move the trigger up a little bit. Oops, got to get we're triggering on a different channel. That's why it's kind of moving around. But yeah, there we go. Now, you see how it's kind of bouncing around? There's this high frequency stuff, but it's kind of bouncing. So let's go ahead and go to get some more cycles, because it looks like there's some low frequency ripple. See that? Yeah, so there's some low frequency ripple there. So I have to stop it here for a minute. And okay, let's get these cursors on approximately, whoops, grabbing the waveform instead of cursors. Okay, so that's approximately on the peak of this -1, and that's approximately there. And it's about 50 hertz, so it's probably the 60 hertz noise coming in through the power supply. So that's probably what that is. So that means we don't have quite enough filtering on the DC power supply, I don't think. We're only pulling 1 amp, 7 watts. So that's kind of a little bit surprising we have that much ripple. Now, it's not very much. I mean, we're 100 millivolts per division, but still, that's a little bit more than I'd like to see. So let's spread this back out again. Look at the high frequency stuff. And I'll freeze it so we can see those. Let's see what frequency the switching power supply is on. Now, there's these major spikes and there's some little ones in between. So that could be on the, I think what the major ones are is the main switching FET turning on. And it could be turning on, turning off here. See how there's another little spike next to it? So, and then there's always kind of a bigger one. And so that could be the regulation. But I think this is a frequency. So, and that's about 52 kilohertz. So that's probably not too far from the truth. Here, let's go ahead and run it. And keep your eye on that. Let's see if it lowers. I'm going to put a small capacitor across terminals. And that looked like, okay, I took it off, put it back on. Yeah, see, that lowers it, right? Then take it off. So what I'm doing is I'm just putting this small capacitor right here. It's just a small XY cap. This 4.7 nanofarad, so it's very small, but you saw what it did. So a little capacitor at the load would help clear a lot of that stuff up. All right, so there's our voltage across this resistor. It's around a 3 ohm resistor. I think it's actually 4 ohms, so we'll be able to get pretty close to max power out. So let's go ahead and bring up the voltage. Now, watch this. I can't bring up the voltage because my current's limited, right? So bring up the current first, and look, we went constant voltage. Okay. I don't hear the fan on this guy yet. I hear it on my scope over there, but not on this power supply, which is really awesome. I smell that getting hot. It's a 300 watt resistor, so it's going to get hot. All right, there we go. And you know what? Look at the ripple over here. It actually looks better than it did with the small load. And you notice there's not, the low frequency stuff seems like it's gone too. So I think that was more of a low frequency regulation thing. Let's try to get more cycles. Yeah, see how that low frequency's gone? I almost think that was because, you know, guys, they see noises down a lot too. So it's a lot. So the noise, I think this meter one goes sleep. So the noise looks a lot better with higher power. Now, let me see how hot these are getting. No, they're not hot at all. So the leads they gave seem to be real copper and seem to be, yeah, they're not warm at all. We've got 7. Oh, what happened? Our current is down to near nothing. 3 watts. All right, let's figure this out. Okay, guys, I was not paying close enough attention. If you see down here, it says 5 amps. So the front terminals are limited to 5 amps. So that's why they have the big old girthy things back here, which I'm using the same wires they gave me, and maybe they're only rated for 5 amps as well. But we'll see. We'll see if it gets hot. Now, this thing did start getting hot at first, but then I think it thermally shut down, and that's what happened. So it'll let you go over 5 amps, but only temporarily. So I'm going to max out the current. Let's bring up the voltage. And if I move the dial fast, it seems like it does accelerate the voltage, so that's good. Okay, 215 watts. And this resistor is still really hot. And there's the waveform. So we do have more noise on there for sure. That's 200 millivolts per division. So I think we do need a little filtration on the output. Now, if you're powering up an amplifier or something like that, you should have capacitors at your input, so you should probably be okay there. Now, as far as low frequency ripple, there's a low frequency ripple. It doesn't look like it's gotten any worse. I think it's just, it might be a regulation thing. I'm not sure. Okay, but this stuff we could clean up. And that resistor is getting very hot. So we're at 216 watts. And these wires are actually still not even really warm. So, yeah. And there's, look how steady the voltmeter is showing. So, it does show, you know, this guy here, It does show very steady. This low frequency ripple, the RMS value, is holding pretty steady. All right, guys, there's the bottom. Here's the rubber feet on it. They twist, so they feel like they're snapped in or maybe screwed in. And there's the fan kind of protruding from the bottom, so that's the way it's installed. So it's back in there, so it's just got a hole in the middle where it protrudes, so mounted pretty secure, I guess. And there it is. So we got vents on both sides, and I've taken the screws out. You're gonna see it for the first time with me. First of all, look inside the lid. Nothing really to see. All right, so what are we looking at here? All right, guys, so let's walk through this power supply. It's pretty interesting. Lots of circuitry. The card up here on the front panel looks pretty nice. Several chips there, some aluminum electrolytic capacitors. So that looks nice. Now, while we're looking at the front panel, this is the potentiometer for the voltage. That looks a very nice, you know, high quality, high turn pot. But then the one for the current is not quite as nice, right? It's too bad the current one wasn't like the voltage one, because I think that's why when I was adjusting the current, I didn't get quite the control. Now here's the terminals for the output voltage, right? Here's the green ground wire going to the board here. But let's kind of walk through the input power. So we come over AC input power right here, right? Now also there's fan power. So right away I see fan power kind of coupled with the AC power here, which let's track that down. So we run up through here with our power, and then our fan power comes from here. It's the fan power is an output voltage regulated off of this. We're going to talk about that in a minute. So we're coupling an AC input voltage with the fan output power. I don't know about that. Not real excited about that. We can take these cables, twist them. They're not twisted either. They should be twisted together, separated, and have their own ties. So then, I mean, there's so much. This looks so nice. It's just kind of too bad that some of those things weren't taken care of. And then this AC power runs across, you know, right through these ribbon cables that are coming up to the front panel. So that's not ideal either. So we come up here with AC power. The black one, the neutral probably, goes down to the one side of this yellow capacitor, the first X cap. So this looks like the EMI filter. This looks like a safety cap, and another yellow one over here. Looks like the bridge rectifier's right here, a little small one, and I'm not sure if this is a current sense transformer or a common mode filter. We could have two EMI filters in parallel, I'm not sure, because we do have that small bulk capacitor. So maybe one of them is for the fan. I'm not sure what's going on there, but this is a common mode choke, and that looks like common mode choke with the small bridge. Yeah, not sure about that. But the red wire comes up here, goes to our power switch, comes out of our power switch, and comes down here to go into that cap, okay? So what do we see here that's not awesome? We have AC power, and here, let me just show you the red and black wire right here coming up to our output terminals. So the AC wires are getting zip tied to the output wires coming back up to these terminals. So I don't know if that's why we're seeing some AC noise ripple on the output. Now over here we see a Y capacitor, that little blue one, and over here we see a couple that are working with this common mode choke. So we have X cap, common mode choke, two Y caps, X cap, and that's another Y cap over there. So I think what we have is two different filters. I think this is a separate filter for something else with the bulk capacitor here. So I think we come out of that, go through this filter, through this bulk capacitor to provide some kind of DC voltage for something. I'm not sure where that goes. If that comes over here to this circuit, I'm not sure what's going on here. This could be another switch mode power supply right here to power all this stuff up here, okay? So that could be what that is. Now, let's just follow the power. So the power comes in here. It looks like it comes up and there's some bulk capacitors. But I think the bridge rectifier must be underneath here to come back to these bulks. And we have a filter here. Oh, no, this is a current sense. See that wire right there? That's a current sense. One wire going in. And around here, it's a toroid. Has 50 turns, maybe 100 turns. So it's a 1 to 50 or 1 to 100 turns. So that way it can sense the current. And underneath this heatsink is some FETs. I'll show you those. So maybe you can see the legs underneath there. It's kind of hard to see them, I guess. But there's some FETs. Looks like there's at least 2 and maybe a couple diodes over here. So the bridge rectifier's over here and a couple of FETs over here, okay? So what's happening is that AC voltage comes in through the EMI filter, comes up here through the bridge rectifier, goes to the bulk capacitors, and then it's getting filtered here. Or then the current's getting read through that current sense right there. And this guy right here might be the drive transformer. It's kind of a big one, though. It might be a drive transformer to the FETs up here, because this right here is the 3525. It's a switch mode power supply regulator chip, a controller chip. And so it's reading current and voltage, the feedback voltage. There should be an optical coupler somewhere between the output, which, so that, yeah, this guy here, this controller, there's a tantalum. See these yellow things are tantalum capacitors. There's one over there. So this guy's controlling these switching FETs, and the main transformer's over here. So I don't know, man, they're kind of scattered around. Over here's the output. So you come off the transformer, see the big wires? So, okay, so you come off the big wires, and then you have a big choke, a couple big chokes here to filter, a bunch of aluminum electrolytics, helps lower the ESR, smooth out the voltage. And then those guys down there, that looks like DC current sense. So there's 3 of them in parallel. And I think that's what it's using to read the current. And then this might be a preload to the output. So when there's no load condition, they help load down the supply. I'm not sure, but that's my guess. And then, yeah, there's a couple more Y caps here in the corner to help filter high frequency. And then you see the big leads coming up here to our output terminals. And then from the output terminals, you see the smaller red and black lead, and that's what's running up here to the front panel. What I want to show you here on the output is, see this big guy? That's a PTC. That's a big old PTC. And what he does is that 5 amp current sense, when he heated up, he shut off. That's the guy that shut us off when I was powering that. So you see the wires coming up here and coming up to the terminals here. Okay. Now, the other thing I didn't point out is, let's go back to the EMI filter. Once you go through the EMI filter, you see this big black guy? That's an NTC, negative temperature coefficient, positive temperature coefficient, this big guy back here. So this one is a resettable fuse. PTC, positive temperature coefficient, meaning it gets higher resistance with current. And this is negative temperature coefficient, meaning it gets lower resistance with current. So initially, he'll block the current to charge these caps, but then he heats up and the resistance kind of goes away. So you get your efficiency back. You're not dropping voltage across him. And then all this circuitry in here is going to all these ribbon cables and all that to the front panel. So this is just a bunch of voltage control. And there might be some feedback in here too from the voltage pot right here. I'm sure that's, this voltage sense here is coming back here. There's a LM324, I believe, is right there. So he's probably helping read the voltage to feedback this guy. Oh, and here's the optical coupler right here, this 4-pin guy. So there's optical coupler. So he's he's feeding the voltage from the output back here, and then this guy here is giving the set point of where we want to do that. So there's some kind of voltage on this resistor providing a comparison to what's coming back on this guy, and that's how you control the output. So yeah, a lot of circuitry here, and all the control stuffs here is nice. What you really want to do, it's too bad that the AC got mixed in with all this stuff. It would have been nice to route this to actually put the switch on this side, keep the AC over here, and just keep the DC all over on this side. So maybe the display could have been moved over a little bit so the power switch could have been on this corner. Keep it away so you're not coupling it with all this other stuff. This is, you know, especially going to the display, I'm sure it's all filtered, but still, yeah, it's not ideal. So, but they are using a lot of nice parts. That's the thing. The current sense like this, you know, all these nice parts. That's, like I say, that looks like a large part, but I think that is the gate drive. So the drive comes from this chip, goes through this, and drives the FETs. So yeah, a lot of nice components. Really nice potentiometer here. Could have put one on the current sense, and you know, nice combo choke here. So there's a cord underneath that plastic, and the plastic's to keep the voltage isolated from the ferrite underneath. And to keep these guys isolated, you have this little bump right here. So you have one set of windings on this side, one set of windings on this side. So this guy is similarly designed, just a different core. You can see there's a plastic bobbin with the winding separated, so combo choke. And this guy down here is a fuse. That's a low current fuse. So this is a low current power supply right here. So that's a housekeeping power supply or auxiliary power supply, whatever you want to call it, but it's just a power, something on the primary side before you come to the secondary side, which all this stuff is. Okay, secondary, that's after it's isolated from the transformer from all this primary power. That's why there's some separation right through here. One more look at everything, and there's the fan. I never heard the fan go on, so I guess you have to have it powered on for a while to heat up enough, which, yeah, so either that or it's a super quiet fan because I never heard it. But that fan's going to blow air across the heat sink, so that's placed nicely. It's going to come down and cool the capacitor at the same time cooling off the output chokes. And you got the transformer, so it's going to hit all this stuff to cool these things off and eventually work its way towards the lower power components up here. All right, guys, so what do you think? A lot of nice components in this. I think if you really were concerned with some of the things I pointed out, keep the AC away from DC, you could just cut the tight straps, maybe even unsolder one of the wires, on the AC side, twist them together. Maybe same with the fan wires, keep them separated, twist them together but separate from each other. And then on the front, maybe I would run the AC along the bottom of the box and then bring it up to the switch, so it's not running in that group of everything else. So I might go ahead and do that. Let me know if you guys are interested in seeing that, because sometimes I do that kind of stuff behind the scene and then I wonder, like, I wonder if I should have filmed that. But yeah, let me know. Never quite sure what you guys are interested in, and what parts are trivial, what parts are interesting. So let me know, okay? Oh, and by the way, the other thing I was going to mention is because the wires go so far from here, from the output terminal all the way up here, it'd be really nice to have a small capacitor across the terminals there for that high frequency stuff to get rid of some of that switching noise. As a matter of fact, since the wires are so small, now they do go through this PTC, which is a resistive element. So even before it opens, it's still got a little bit of resistance. So when you put a capacitor up there, it's really going to benefit. You're going to have an RC filter. So yeah, especially if you want something as big as a 1 microfarad. You don't want to go too big, because when you turn off power, you don't want to have to discharge that cap to your load. So, but yeah, definitely a smaller capacitor up here on the front terminals. As a matter of fact, back here on the back terminals, same thing. Once you come off the board and you run wires, say 2-3 inches. You got 2 or 3 inches on red, 2 or 3 inches on black. You got 5 or 6 inches total. It'd be nice to have a little capacitor there, another RC filter, if you will. So it's just high frequency stuff to get rid of some of those high frequency spikes you see, and it really helps. So yeah, there you go. Now, a lot of times when you're powering up something, an amplifier or whatever, it's going to have input filtering. So those high frequency spikes, they're very low energy. So they're fairly easy to filter. It's the low frequency, 60 hertz, 120 hertz, that takes the larger components and takes more filtering. It's really fairly simple to block out that high frequency stuff. So, all right, guys. 2 thumbs up to my patrons as always. 2 thumbs up to the members. I've only got a few members, but I really appreciate you guys. It's really cool. So thanks a lot. And for those that you've hit that super thank you button, I appreciate that as well. Buy me a cup of coffee, whatever. All right, guys. Thanks for watching and appreciate you. And a free way to support the channel, which really helps a lot, is give a thumbs up, okay? And if you're not a subscriber, subscribe. That helps a lot. I just hit 25,000. That's really awesome. But I want to grow the channel, so I get more stuff like this, things like that when I get likes and thumbs up and that kind of stuff. YouTube shares it and really supports the channel. So really appreciate that. Thanks for watching. We'll see you next time.